All right, let's try to set up one more differential equation with series solutions. And in this example, we're going to be thinking about solving y double prime minus 1 plus x y equal to 0. And I'm just going to note that for x0 equal to 0, we have convergence for all x between minus infinity and infinity, because the functions p equals 0 and q equal minus 1 plus x, neither of them breaks anywhere. So this is a well-behaved problem. We're only going to solve well-behaved problems. But so we're given that differential equation, and I'm going to go ahead and plug in my solution y and derivatives as series. So y double prime is n equal to infinity times n minus 1 cn x to the n minus 2. And I've got minus 1 plus x times y, but y is going to be that sum from n equals 0 to infinity of cn x to the n. And I want to combine these two series. The first thing I'm going to do is get my powers x to match. So I need to make sure that I distribute any powers x from outside before I start. Otherwise, that can cause problems for me later. So distributing across to this series is going to give me minus n equals 0 to infinity cn x to the n. That's just from the 1. But then when I multiply by x, I'm going to get cn x to the n plus 1. So this is x to n times 1 right here. X to n times x turns into x to n plus 1 right here. So in this problem, I have 3 different series that I'm trying to combine. And first things first, I need to get their powers the same. I'm going to try to take them all to x to n. You really could pick any number you want to. That's just the one I like the most. So for this first sum, if I'm going to be going to x to n, that means that I'm going to have to go ahead and add 2 to everything inside. So I'm trying to do this example instead of using that checking the bottom like I normally do. I'm going to do the add and subtract just so you see it a different way. Since I added inside my series, I need to subtract outside my series. So it goes from 2 to 0. This middle series is already power x to the n, so I don't have to do anything. And then this last series, if I want to go from n plus 1 to n, that means I'm taking away 1. So then the cn becomes cn minus 1. And since I'm taking away inside, I need to add outside. So my n equals 0 becomes n equals 1. Same approach as the first one we did. And you'll get used to doing this one on the left because you do it a lot. This one changes a little bit every time. You know, there's like a different function that we're multiplying times the y prime or y. Now I need them all to have the same index. And you could go ahead and move this one down to 0. But for me, it's always hard to think about subtracting. So instead, I'm just going to move both of these up to 1. So for this first one, if I move that up to 1, I just have to write out the 0 term in front. So 0 plus 2 is 2, times 0 plus 1 is 1. Plus c sub 0 plus 2 is c2 times x to 0. And then here, when I shift this series, I'm going to be really careful to note that it's minusing that whole series, so I need to make sure that I also minus the thing I throw out front. That's why I added those big square brackets for a second. So this one is going to become n equal 1 to infinity cn x to n. But in order to make that true, I need to get rid of my n equals 0 term. So that's c0 x to 0, which should be added to the whole series. And then my last series is already fine. It's from 1 to infinity, cn minus 1 x to n already. So I'm going to want to group everything that's outside the series and then put everything into that one common series. So this is going to give me 2c2 from my first term here, minus c0 from the second term here. Don't forget about the minus sign that's coming in. And then I'm going to have a big series from 1 to infinity that has power x to n. And I'm just going to put everything that was inside all my series that are ready to combine. So I had n plus 2 times n plus 1 times cn plus 2. And then I got to do minus this series. Do not forget to distribute your negatives. Minus cn. And then minus my last series, cn minus 1. And so for this problem, my two relationships are going to be that 2c2 minus c0 should be equal to 0, and that all of this stuff should be equal to 0. So I set everything outside the series equal to 0, and I set everything that multiplies x to n inside the series equal to 0. I will need to be moving to the next slide in a second, but go ahead and pause if you need a bit more time to fill that in. When I actually solve for these things, I get that the first relationship told me that 2c2 minus c0 is 0, so c2 is just c0 over 2. And then the second one told me that big old mess of things, but I'm solving for cn plus 2 in terms of everything else, so I just move these over and divide by the n plus 2, n plus 1. You always want to solve for the higher c in terms of the lower c, because we always start low and start increasing. So it would be harder if you did it the opposite way. So I'm going to get that this should be cn plus cn minus 1, all of it divided by n plus 2 times n plus 1. And a lot of the time it's going to help us to represent that with different letters. K. Like that. And at this point, I've set up the relationships I'm going to need. This is everything that is left to be filled out in the skeleton notes. And I know that finishing this problem would make this series of videos very long and difficult to watch. So if you have reached the end of what you can think about for series, go ahead and leave. I'm going to work through the rest of this problem though, and I actually want to point out something about coefficients that sometimes comes up for needing to represent them in terms of a specific index. So just so you know, if I wanted to write just ck, a function for the current value k, instead of doing that thing where I like plug in different values, like I say, oh, I want c3, so I better plug in k equals 1. Suppose you want to shift it so that you just have every time the formula 4 being at c3. We can use that same argument we use to shift series indices to say, okay, that would mean I take away 2 from my k. So everywhere on the right where I see k, I just take away 2. That means I look at c k minus 2 plus c k minus 2 minus 1 is minus 3 over k minus 2 plus 2 is k, and k minus 2 plus 1 is k minus 1. You can also manipulate your formulas into this form in order to plug them in maybe more easily when you're solving problems. So we're going to go ahead and work through the rest of this to get to the fundamental solutions and general form of the solution. Again, no pressure, leave if you need to. And I'm going to actually go ahead and just take this back to being in terms of n's because I like them more. So I just renamed k to n again because that's always something we're allowed to do. And I'm going to write out the first few n's we're going to be doing. We might need to shift those down as we go. But so for n equals 0, I'm trying to find C0. This relationship has C0 in it, but it also has C2, so I don't have enough information to use it yet. And this one requires that I know two C's before me, so I can't use that either. Sorry, I said either twice. I can't use that yet either. So I'm just going to go ahead and say that C0 is C0. Same reasoning has us start with C1 equals C1. And then once we get to C2, we have our two unknown constants, so we can't keep any more unknown. And for this one, I'm going to go ahead and note that this is an equation about C2. It's C0 over 2. I'm using R1 for that. And then when I get to n equals 3, I want to know C3. And I can't use this one anymore. And I can't use unknown constants anymore, like I can't introduce new ones. So even though it looks pretty messy, it means I'm probably using this one down here. So I'm going to go ahead and try it out. I have n equals 3, so I'm doing C3 minus 2 plus C3 minus 3 over 3 times 3 minus 1. That's going to be C1 plus C0 over 3 times 2. And I'm actually even going to go one step further and break this up into the things that have C0 and the things that have C1. Still not simplifying my denominator, but I know eventually my solution is going to have all C0s and all C1s, so I do want to note them separately. Then when I get to C4, I'm going to use my formula again, 4 minus 2 plus C4 minus 3 over 4 times 4 minus 1. That's going to be C2 plus C1 over 4 times 3. And then C2 was C0 over 2, so that's going to be C0 over 2 times 4 times 3 plus C1 over 4 times 3. And then when I get to n equals 5, I'm going to be calculating C5. That's C5 minus 2 plus C5 minus 3 over 5 times 5 minus 1. So that's C3 plus C2 over 5 times 4. Okay, this is where it starts to get a little bit complicated. So my C3 was C0 over 3 times 2, so now I've got 5 times 4 times 3 times 2, plus C1 over 3 times 2, so 5 times 4 times 3 times 2. And then that was all C3. I just copied this and moved it down and added my 5 times 4. I still need my C2, so that one is plus C0 over 5 times 4 times 2. I need to move to my next slide. So hit pause if you're still with me and still working. But I didn't have quite enough room to finish my C5. So if I want to combine these two C0 terms, they do have to have the same denominator. So I'm actually going to turn this one into 3 C0 over 5 times 4 times 3 times 2. I'm just writing down that change that I told you I was going to make. And then 3C0 plus C0 is just 4C0 over 5 times 4 times 3 times 2 plus C1 over 5 times 4 times 3 times 2. Hopefully you've got that copied down. Now that I'm seeing something weird happening with my C0s and my C1s, I'm going to go back real quick and note last time I had differences between my C0 and C1 was here when I did C4. You know, I had to add in that C0 over 2 from C2, and it didn't affect the C1. But I didn't really pay attention to things being different because I didn't have weird terms to merge. But this one, if I cared about that, I could write 4 times 3 times 2 plus C1, 2 over 4 times 3 times 2. Just so that they have the same denominator, because I'm starting to at least see that there's a factorial in the denominator of all these different terms. So we could go ahead and try another one, see what happens. So C6 from my formula is going to be C6 minus 2 plus C6 minus 3. All divided by 6 times 6 minus 1. So that becomes C4 plus C3 over 6 times 5. And I know you might still be writing that down, but I got to go back and see C4 and C3. So I'm going to go ahead and copy them. That way I can take you back to the slide you care about. You know, all 3 of you that wanted to watch the optional video. So C4 is this lower one. It's my C0 over 4 times 3 times 2. But now I have to add that 6 times 5. Plus that 2C1 over 6 times 5 from the new term times 4 times 3 times 2. And then C3 was this one up here. So that's my plus C0 over 6 times 5 times 3 times 2 plus C1 over 6 times 5 times 3 times 2. I'm going to be trying to combine like terms. So that's going to be C0 over 6 factorial plus 2C1 over 6 factorial plus, I'm missing a 4 in the denominator, so 4C0 over 6 factorial plus 4C1 over 6 factorial. So that's 5C0 over 6 factorial plus 6C1 over 6 factorial. And so there is a pattern to this where my C0's gone from 4 to 5 here. My C0 and my C1 went from 1 to 6. So there's something odd happening in the numerators, but I definitely have those factorials in the denominator. So if I wanted to write y equal to C0 times a bunch of stuff plus C1 times a bunch of stuff, I'm gonna get that my C0s start just at C0. So that's my 1. And then I see it again in my x squared term. So that's going to be plus x squared over 2. And then again in my x cubed term, which I'll note that this is 3 factorial, and even 2 is 2 factorial. And then in C4, I had C0 over 4 factorial. And in C5, I had C0 4 over 5 factorial. And in C6, I've got 5 x to the 6 over 6 factorial, and you could keep going. For C1, it first appears in that n equal 1 term, so that's power x. And it didn't appear in x squared because that only depended on C0. So then we next see it in our third term, right here, just over a regular 3 factorial, plus 2x to the 4th over 4 factorial, plus just x to the 5th over 5 factorial, plus 6x to the 6th over 6 factorial, so on and so forth. I know, it's a long problem. And I showed lots of examples so you could see them calculated, but if you wanted to stop after the first few, that would be okay. Just I wanted to show that it was kind of getting more complicated as we went on because of that weird definition of C0. But at this point, we have a solution. It's a general solution with 2 unknowns, and these 2 things in brackets again are our fundamental solutions. So we would say that we're done with this problem. If you stuck through to the end, nice work. I hope you feel more confident about series than before you stuck to the end. And this is our last video, so I will not see you next time.